Okay, I just want to talk about your most recent quiz. So this is quiz 4.1 through 4.3. And so what I wanted to say about it is that when I first started working it out, I thought to myself, oh man, this is, I kind of expected you to do a little bit worse on this quiz than you ended up doing. Actually, you surprised me and you did really pretty well on the quiz as a class overall. However, I thought that I would walk you through it anyway because there were a couple of you who, uh, based on what I saw in your quizzes, seem relatively confused about how to go about these kinds of problems. The other thing that I wanted to point out is that I didn't really give you a ton of space to work out your solution, and so you need to be I guess strategic about the way that you use space, and so so I'll say a little bit more about that in a second. But let me just show you how I would go through this problem, okay? And I'll point out some of the common mistakes that I saw. Um, so first of all, it says find all critical points and inflection points of f. I'm going to find the critical points by looking at f prime, and I'm going to find the inflection points by looking at f double prime. So I know that there's going to be some differentiation here. It also says to identify any relative extrema. And so in order to do that, I have to either do a second derivative test, which actually nobody did on the quiz, which is fine. You don't have to do that. Or I have to do the first derivative test, which involves making a sign chart to figure out where f is increasing and decreasing, right? But anyway, let's get to it. So let's go ahead and find our derivatives. So f prime. Now, some of you are still showing a ton of work when you go to take derivatives, and at this point you really just need to start doing some of this work in your head, okay? Here I've got the sum of two monomials, and those are easy to differentiate, right? You just multiply the exponent by this number and then subtract one from the exponent. You don't need to write down a whole bunch of steps here. Just do 5 times 2/3 is 10/3, and 2/3 minus 1 is negative 1/3. Okay, that's the first term. And then the second term, 5/3 times 1 is 5/3, and 5/3 minus 1 is 2/3. And there's your derivative, right? That's all there is to it. Um, Now, if I want to identify the critical points, then I need to set this thing equal to 0 and solve. And actually, what I need to do is look for two things. I need to look for where this derivative is 0 and where this derivative is undefined. Okay? So that's usually going to involve some factoring. In this case, I know I can take out 5/3, and I also know that I can take out an x to the negative 1/3. And if I do that, then I'm left with 2 plus, um, I took out the 5/3, x to the 2/3. If I subtract a negative 1/3, then I'd be left with x to the first power, right? So there you go. Or divide by an x to the negative 1/3. So I subtract the exponents, right? 2/3 minus negative 1/3 is 1. So there you go. And now if I set that equal to 0, or actually, let me take it one step further, because um, I can rewrite this as 5 times x plus 2 over 3x to the positive 1/3. And the reason I do that is because it is just to point out that, hey, look, there is a place where the derivative is undefined, because it's going to be undefined wherever this expression is, wherever the denominator is 0, right? So f is not differentiable when x equals 0, because the derivative is undefined there, right? So that's one critical point. And then the other critical point is when the function is equal to 0, and that happens when x equals negative 2, okay? So I can list my critical points. They are 0 and negative 2, right? Negative 2 is a stationary point. 0 is a place where the function is not differentiable. And so those are both critical points. Now, I was asked to identify any relative extrema, which means that I need to see. So remember, your first derivative tells you where you have relative extrema potentially, and so I need to test to see whether these things are maxima, minima, or maybe neither, okay? And I do that by either making a sign chart, first derivative test, or by taking second derivative and running the second derivative test, which sometimes is inconclusive. Personally, I prefer the sign chart. And like I said, none of you did a second derivative test on this one, so I'm just going to go ahead and make the sign chart, okay? So I need to test the interval going from negative infinity to 0, and then from 0, oh, I'm sorry. I need to put these in order. I need to test the interval going from negative infinity to negative 2, and then from negative 2 to 0, and then from 0 to positive infinity, okay? I'm going to test those intervals by plugging in some test point in this interval into the derivative f prime, and that will tell me where f is increasing and where f is decreasing, right? So, so I'm going to look at the sign of f prime. So if I plug in a test point here, like negative 3, I'm going to plug this into my derivative. Negative 3 plus 2 is a negative number, and negative 3 to the 1/3 will also be a negative number. Okay, so I'm going to be positive in that region. And then I can write a little conclusion or whatever. Okay, so my conclusion here would be that I'm increasing on this interval from negative infinity to negative 2. Now I can plug in a test point between negative 2 and 0, like negative 1. If I plug in negative 1, I'm going to get a positive up here, still a negative down here. That'll make f prime negative, which means f is decreasing. And then a test point in here, like 1. I'll have a positive here, a positive there. That makes f prime positive, which means f is increasing. Okay, now what does that tell me about maxima and minima? Well, it tells me that if I'm going from so I'm increasing from negative infinity to negative 2, and then from negative 2 to 0 I'm decreasing. So I must have a maximum, right? So I've got a maximum at x equals negative 2. Now to see what the y coordinate of that maximum is, I can plug negative 2 into the original function f, and I've already done this, so I'm just going to go ahead and say that, so I would do f of negative 2, right? Not f prime of negative 2. I would plug it into f, but you're going to get approximately negative 2, 4.76, right? It's approximately 4.76. So I have a maximum there. That's just from this stuff. And then from here to here, I went from decreasing to increasing. So I must have a minimum, right? It must be a minimum at 0, f of 0. Well, when I plug in 0 to f, I just get 0, right? So that's the point 0, 0. So I've got a maximum at negative 2, 4.76, and a minimum at 0, 0. Good. So that takes care of my critical points and my relative extrema. Now, I also need to find the inflection points, and that requires me to take the second derivative. Now, a lot of you, when you took the second derivative, you used this format of the first derivative, and then you used quotient rule. That's not wrong, but that's an awful lot of work. Because, look, I can just use this version, and then I don't have to use the quotient rule, right? I'm just going to use this version right here, and I'm going to say, all right, f double prime, and then I'm going to do the same thing. I'm not going to show a ton of work, okay? I'm just going to do a lot of this in my head. I'm going to say, all right, so I'm going to take negative 1/3 times 10/3. That's going to be negative 10/9. X to the negative 1/3 minus 1 would be negative 4/3. And then I do the same thing with the second term, right? 5/3 times 2/3 is 10/9. X to the 2/3 minus 1 is negative 1/3. Okay, and that's all there is to it, right? There's your second derivative. Easy, easy squeezy, right? Okay. But I need to set this thing equal to 0 and then solve so that I can find any potential inflection points, right? So I'm going to do the same trick as before. I'm going to factor out a 10/9, and I'm going to factor out an x to the negative 4/3. If I do that, then I'm going to be left with a negative 1 for that first term. And for the second term, I'm going to be left with a positive x, right? Negative 1/3 minus negative 4/3 is 1. Okay, and so rewriting this, I'm going to have x minus 1, 10 times x minus 1 over 9 times x to the positive 4/3. And so once again, I find that potentially I have inflection points at 0, because that's where the second derivative is undefined, and at positive 1. Okay? In order to see if they're inflection points, I need to make another sign chart, right? So 0 and positive 1, right, are my possibilities. So I'm going to make a sign chart. I'm going to test the interval from negative infinity to 0, and then the interval from 0 to 1, and then the interval from 1 to infinity. Okay? And this time I'm looking for the sign of f double prime, right? I'm looking for the sign of the second derivative, and that'll tell me what the concavity is. Okay? That'll tell me what the concavity of f is. So let's see. If I plug in a test point here, like negative 1, I'll have a negative. Here I'm always going to get positive, right? Because I'll take the cube root, but then when I raise something to the fourth power, it's always going to be positive. So this is going to be negative, which tells me I'm concave down. Okay. If I plug in something between 0 and 1, like 1/2, 1/2 minus 1 will still be negative. This will still be positive. So this is still negative, so I'm still concave down. And then if I plug in something between 1 and infinity, like 2, this will be positive, this will be positive, and so that'll be positive, so I'm concave up. Okay, so remember, an inflection point is where you change concavity. I only change concavity here, right? That happens when x equals 1. So I've got an inflection point at 1, and then to find what the y value is, you would plug 1 into the original function f, and if you do that, you get 6. So you have an inflection point at 1, 6. Okay, and that's it for part A. It's a little cramped on space, I'll admit. I could have given you a little bit more room, I guess, to work it out, but that's the idea. And you know, if you're not showing an unnecessary amount of work, then it should be plenty of space to get the job done. So when I say an unnecessary amount of work, now if this was yours, try not to feel embarrassed. This is just a learning thing for everyone. But here's what I mean by like an unnecessary amount of work. So like all of this stuff, all along this row, is just calculating the first derivative. In fact, this student didn't even finish calculating the first derivative until the top of the next line. Now, I think that is the correct solution as it turns out, but holy schmoly, you don't have enough space on your quiz to show that much work for the first derivative. Okay, you just don't. Here's another student. This one wasn't quite as bad, but still, you know, taking like three lines, you know, to find first derivative. It's like you just don't. You need to be a little bit more economical in your use of space. Do some of this work in your head, right? You can do some of the work in your head. Okay. Now, when it comes to graphing this thing, so part B says, use your work in part A to sketch a graph of f. Be sure to plot all x-intercepts. Well, I didn't find the x-intercepts in part A, so I better find them in part B. I'm going to factor f, right? Remember, f of x is this thing, 5x to the 2/3 times x to the 5/3. So I can factor out an x to the 2/3. And then I'd be left with 5 plus x, right? 5/3 minus 2/3 would be 3/3, which is 1. So that tells me that I've got x-intercepts at 0, 0, and at -5, 0. Okay, so let's plot those things, right? 0, 0 is an x-intercept. -5, 0, 1, 2, 3, 4, 5 is an x-intercept. 1, 2, 3, 4, 5, 6, 7, 7. 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7. Okay, good. What else do I know? I know that I've got an inflection point at 1, 6, 1, 6. So that's an inflection point. I know that I have a maximum at -2, 4.76. So -2, 1, 2, 3, 4.76. So right about there is a relative maximum. And that's all I really know for now. However, I also know a little bit about concavity, right? Like, I know that from -infinity to 0, I'm concave down. So I know that I'm concave down from there to there. Okay, gotta be. And so if the graph kind of turned over like this, that would change concavity, right? I would be concave up over here. I know that that doesn't happen. I know that I'm just concave down, and so I know that this must continue on down to -infinity like that. Okay. Now, if you're a little shaky on that, then what you could do is look at the end behavior. You could say, well, actually, what is the limit as x approaches -infinity of f of x, right? And so you could imagine plugging in larger and larger negative values here. Now, interestingly, when you square this, this will become a positive infinity. But because this exponent is larger than that one, it's going to dominate, and so it's gonna cause f to go down to -infinity. There are some details there that you can kind of work out, but it's not totally necessary to even show that, because you're really just trying to convince yourself that this is true, right? That you're going to be shooting down all the way down to -infinity. I know that I'm still concave down from 0 to 1, and that's really interesting, right? If I'm concave down, then the curvature must be something like that, right? From 0 to 1, because I have to be concave down. And then finally I switch to be concave up from 1 to infinity, and so that's where I have my inflection point, and it changes to being concave up. So based on my work, right, with my inflection point there, my maximum there, my minimum there, this is what I'm suspecting that the function should look like. Now, in order to verify that this goes off to positive infinity, again, you could check the end behavior there. You could look at the limit as x goes to positive infinity of f of x, and you should get positive infinity. Okay. The other thing that you might be a little bit uncertain of is, like, do we really have this weird cusp here? And we talked about this in the lecture as well. We said that in order to determine if you have a cusp, what you should do is look at the limit as x approaches 0 from the left, look at the limit as x approaches 0 from the right, but not of the original function f. You should look at that. You should look at those limits for f prime, right, for the first derivative. So in other words, you should look at limit as x approaches 0 from the left of f prime of x, and you should look at limit as x approaches 0 from the right of f prime of x. And if one of them is going to -infinity and the other one is going to positive infinity, then you know that you've got a cusp. And that actually turns out to be the case here, right? Limit as x approaches 0 from the left of f prime is -infinity, and limit as x approaches 0 from the right of f prime of x is positive infinity. And I'll let you work out the details there. Again, not totally necessary to even do this, because just based on what we know about the concavity, the maxima, the minima, we know that the graph must look like this. And again, you can verify it on Desmos, right? That this is in fact the case. So that's all that's all I really expected you to kind of do here. I wanted to just show you, because I showed you a couple of students who maybe showed a little bit too much work or whatever. Let me show you a couple of really good solutions, just so that you know that, like, you're not horrible students or whatever, and you're not a horrible class. Actually, like I said, I was pleasantly surprised at how well you actually did on the quiz. But there were a couple of really good solutions, nice and neat, right? Showing everything they need to show, right? Giving me a very beautiful, perfect looking graph, right? It's very good. Same way here. So this student does their work on a separate sheet of paper, and then they just upload the image, which is perfect, right? You can do that if you want. Anyway, but again, like, perfect amount of work, showing the sign charts, like, very neat, very organized, nice looking graph. Um, so, um, well, actually, the graph is kind of, I guess now that I'm looking at it more closely, the graph should be the other way around, right? Like kind of like that. But anyway, uh, but good stuff. So I think that's all I have to say about that.